A critical system failure often starts not with a crash, but with a creeping increase in latency. Imagine a high concurrency logging system designed for 10,000 events per second. Initially, everything looks perfect, but as the data volume grows, the disk I/O wait time spikes, and the system eventually stops responding. This is the classic write amplification trap found in traditional B-tree-based engines. When every small log entry requires a search for a specific disk page followed by a random write, the physical disk heads or even SSD controllers hit a saturation wall. The overhead of maintaining a sorted, balanced tree in real time under heavy write pressure creates a performance cliff that no amount of horizontal scaling can easily fix. You might throw more memory at the problem, but the fundamental bottleneck remains at the storage layer. But why does a structure that worked for decades suddenly buckle under the weight of modern telemetry? The answer lies hidden within the disk head itself, and how our software talks to our hardware. To prevent these system performance collapses, we must treat the database not as a black box, but as a sophisticated arrangement of storage engines. The decision you make between an LSM tree and a B-tree determines the upper limit of your architecture's scalability before you even write a single line of application code. In this lecture, we are going to strip away the SQL abstraction and dive into the mechanics of data persistence. We will explore how OEL ensures durability, how memtables handle high-speed ingestion, and how SS tables transform random writes into efficient sequential streams. Mastering these internals allows you to predict when a system will fail and choose the right engine for the specific workload, be it read-heavy, write-heavy, or a complex hybrid. By the end of this deep dive, you will have the framework to evaluate any database engine based on its internal storage strategy rather than just its marketing features. To understand the fix, we must first strip away the abstraction of SQL and look at what actually happens when a byte hits the persistent layer. What exactly is a storage engine? In the standard database architecture, it is the lowest layer that interacts directly with the operating system's file system or raw block devices. While the query optimizer handles how to find the data, the storage engine handles how to store and retrieve the bits. It provides a clean API usually consisting of get, put, delete, and scan operations to the higher-level database management system. Under the hood, it manages incredibly complex tasks. It implements concurrency control to prevent data corruption, maintains the buffer pool or page cache for performance, and ensures the atomicity and durability of transactions through logs and checkpoints. Whether you are using MySQL with InnoDB, PostgreSQL with its heap files, or RocksDB as an embedded store, the storage engine's efficiency in translating logical operations into physical disk I/O determines the latency profile of your entire stack. This abstraction is powerful, but it hides a fundamental conflict. Hardware prefers sequential access, while software often demands random updates. The evolution of storage engines is a history of adapting to hardware realities. For decades, the B-tree was the undisputed king. Introduced in the early 1970s, it was optimized for spinning hard drives where seeking was expensive, but once the head was positioned, reading a sorted page was efficient. B-trees provided a stable, O-log-n performance for both reads and writes, making them the standard for relational databases like Oracle and SQL Server. However, as internet-scale applications emerged in the mid-2000s, the write-heavy nature of social media, sensors, and logs exposed the B-tree's weakness, random write overhead. This led to the rise of log-structured merge trees, or LSM trees. By buffering writes in memory and then flushing them as large, sequential blocks to disk, LSM trees revolutionized high-concurrency ingestion. From Google's Bigtable to Facebook's Cassandra and RocksDB, the shift toward LSM trees represents a move toward prioritizing write throughput and SSD-friendly sequential I/O. In the next chapter, we will dissect the B-tree, the titan of the relational world, and see exactly where its limits are drawn. To understand why B-trees dominate the database landscape, we must first look at their physical DNA, the page. Unlike simple arrays, a B-tree organizes data into fixed-size blocks, typically 4 KB or 16 KB, which aligns perfectly with the underlying operating system's page cache and disk sectors. This hierarchical structure consists of root nodes, internal nodes, and leaf nodes. The leaf nodes are where the actual data, or pointers to rows, reside, and they are linked together to facilitate fast-range scans. This design is built for stability. It ensures that the tree remains balanced regardless of how many records you insert, maintaining a consistent depth across the entire structure. In a technical sense, this is the realization of global ordering maintained at a high cost of structural management. But how does this rigid, page-based structure actually translate to the lightning-fast lookups we expect in a high-concurrency production environment? The primary strength of the B-tree lies in its search efficiency, specifically its O-log-n complexity. When a query arrives, the engine starts at the root page, performs a binary search within that page to find the appropriate pointer, and descends to the next level. Because the fan-out or the number of pointers per page is typically very high, even a database with billions of rows usually only requires a tree depth of 3 or 4 levels. This means a random point lookup requires only a handful of page reads. For read-heavy applications where users are frequently fetching specific profiles or product details, this predictability is invaluable. It minimizes the number of disk seeks required to locate a needle in a haystack. This efficiency is precisely why we favor B-trees for read-heavy workloads. But what happens when we need to modify that data using the in-place update model? B-trees operate on the principle of update in place. When you update an existing record, the database engine locates the specific page on disk, brings it into memory, modifies the bits, and eventually writes that same page back to its original physical location. While this keeps the index compact and the search path short, it introduces significant overhead. If a page is full and you try to insert more data, a page split occurs. The engine must allocate a new page, move half the data, and update the parent pointers all while holding latches or locks to ensure concurrency control. Over time, frequent updates and deletes lead to fragmentation, where pages are only partially full, wasting valuable disk space and memory. Overwriting sounds simple, but physically, it is the beginning of a massive performance bottleneck on modern high-speed hardware. Do you see the trap here? This design assumes a disk can handle these scattered writes effortlessly. In the world of storage, not all writes are created equal. B-trees inherently rely on random writes because data is inserted based on its key value, not its arrival time. On traditional HDDs, this meant constant mechanical head movement or disk seeks, which are agonizingly slow. You might think SSDs solve this, but even modern NVMe drives are optimized for sequential throughput. Random writes trigger internal housekeeping within the SSD's flash translation layer, leading to higher latency and shorter drive lifespans. When your write volume scales, the B-tree engine spends more time waiting for the disk arm or the flash controller than actually processing data. This is the fundamental trade-off. B-trees give you consistent read performance at the cost of high latency, random write patterns. If random writes are this expensive, how do B-trees manage to guarantee that your data is safe, even if the power cuts out right in the middle of a page split? To bridge the gap between slow random writes and the need for data safety, B-trees utilize a write-ahead log or WAL. Before any changes are made to the actual B-tree pages, the intended changes recorded in a sequential, append-only log file on disk. This is a critical architectural pattern for durability. If the system crashes, the engine can replay this sequential log to recover any lost in-memory updates. However, notice the duplication. Every write must happen twice, once in the WAL and once in the B-tree page itself. This is often called double write overhead. While it ensures AC compliance, it reinforces the fact that B-trees are fundamentally not designed for high-velocity write ingestion. They prioritize the structure of the data over the speed of recording it. Now that we understand the mechanics and the overhead, let's see which giants of the industry decided this was the right trade-off for their architecture. Despite the write bottlenecks, B-trees remain the default choice for the world's most trusted databases. PostgreSQL uses it as its primary index type for its stability and excellent range scan performance. MySQL's InnoDB engine is built entirely around a clustered B-tree index, ensuring that primary key lookups are as fast as possible. Even SQLite, which powers millions of mobile apps, relies on B-trees for its simplicity and reliability. These systems dominate the read-heavy world because most business applications from banking to e-commerce read data far more often than they write it. For these use cases, the B-tree's log-n read guarantee is the gold standard. However, as we enter the era of big data and high-frequency IoT sensors, there is a breaking point where this in-place model simply cannot keep up with the incoming flood. This is where the LSM-Tree enters the stage, and it flips everything we just learned on its head. While B-trees represent the standard for read-heavy workloads, they face a fundamental physical limitation when dealing with high-velocity write traffic: the overhead of random I/O. Every update in a B-tree requires an in-place modification, often forcing the disk head to move across various sectors to update specific leaf nodes. In contrast, the log-structured merge tree, or LSM-Tree, revolutionizes this by treating all incoming data as an immutable sequence of events. Instead of searching for the exact location of a record to update it, the engine simply appends the new version of the data. This transformation of random writes into sequential appends allows systems to achieve near-theoretical maximum disk throughput. In modern distributed systems handling millions of events per second, this sequential approach is not just an optimization, it is a necessity for survival. But how can we maintain order in a system that only appends data? The answer lies in the volatile memory layer we call the memtable. But wait, if we only append, how do we prevent the system from becoming a disorganized mess of duplicates? The secret is in the sorting phase occurring right now. The journey of write operation begins in the memtable. When a PUD request arrives, the engine first records the change in a write-ahead log (WAL) for durability, then immediately inserts it into the memtable and in-memory sorted data structure. Most high-performance implementations, like those found in RocksDB or LevelDB, utilize a skip list or a red-black tree for this purpose. These structures allow for a log-n search and insertion while keeping the data perfectly sorted in RAM. By maintaining this order in memory, we bypass the need to sort data later on the much slower disk. This phase is critical because it acts as a high-speed buffer, absorbing the bursts of write traffic that would otherwise choke a traditional B-tree. However, memory is a finite and volatile resource. As the memtable reaches its capacity, typically between 64 MB and 120 AMB in production environments, it must transition to a more permanent state. But what happens to the incoming writes while the engine is busy writing this data to disk? We are about to see the freezing mechanism that ensures zero downtime ingestion. Once the memtable hits its predefined size limit, it is marked as immutable and a new, empty memtable is swapped in to handle incoming traffic. This freezing process is instantaneous, ensuring no interruption to the application. In the background, a flush thread takes this frozen memtable and writes its entire contents to disk as a sorted string table or S table. This file is 100% immutable. It will never be modified again. The SS table format is highly optimized, consisting of sorted data blocks and an index at the end for quick lookups. By flushing data as sorted blocks, we create level 0 of the LSM tree. Each flush creates a new file, meaning the same key might exist in multiple SS tables if it was updated multiple times. This leads to a fascinating problem. If the data is fragmented across many files, how do we find the most recent version without checking every single one? This is where the inherent red penalty of LSM trees begins to surface, and it is the price we pay for such incredible write speeds. Let's examine how we manage this search complexity. The greatest strength of the LSM tree, its append-only nature, is also its greatest weakness when it comes to reads. Unlike a B-tree where a single tree traversal leads you to your data, a read in an LSM tree might require checking the active memtable, then the frozen memtables, and finally multiple layers of SS tables on disk. This phenomenon is known as read amplification. Because the data is spread across multiple files, a simple point lookup for a specific key could theoretically result in multiple disk I/O operations. If a key doesn't exist, the engine might exhaustively search every single S table before concluding it's not there. In a system with thousands of S tables, this would be catastrophic for latency. Therefore, the architectural challenge shifts from how do we write fast to how do we skip irrelevant data even faster. This brings us to a beautiful mathematical solution that allows us to peek inside a file without actually opening it. Do you know how we can prove a key ISNT in a file with almost zero cost? Let's look at the Bloom filter. To combat read amplification, LSM-based engines employ Bloom filters. A Bloom filter is a space-efficient probabilistic data structure that can tell us with 100% certainty if a key is not in an SS table. When an S table is created, a Bloom filter is generated for all the keys it contains and stored in memory. When a read request arrives, the engine first queries the Bloom filter. If it says no, we skip that disk I/O entirely. If it's maybe, we proceed to read the file. While there is a small chance of a false positive, where the filter says maybe but the key isn't there, the savings in disk I/O are massive, often reducing unnecessary reads by over 99%. This is why databases like Cassandra can maintain high performance even with massive datasets. However, while Bloom filters solve point lookups, they don't help with range scans where we need to read a sequence of keys. To keep range scans and long-term performance stable, we need a way to merge these fragmented files back together. But before we get to that maintenance, let's see which famous databases are actually using these LSM trees today. The LSM tree architecture isn't just a theoretical concept, it powers the world's most scalable data stores. Apache Cassandra uses it to handle petabytes of data across global clusters, where write availability is paramount. RocksDB, developed as an embeddable persistent key value store, is used as the storage engine for everything from MyRocks, a MySQL variant, to modern streaming platforms like Apache Flink. Even ScyllaDB and LevelDB rely on this core logic to provide high concurrency performance. When you choose an LSM-based database, you are making a conscious strategic trade-off. You are prioritizing write throughput and disk space efficiency over the predictable read latency of a B-tree. However, as the number of S tables grows, the system's performance will eventually degrade unless we perform constant house cleaning. This process of merging and purging data is what keeps the engine alive. In the next chapter, we will dive into the most computationally expensive part of the LSM engine, compaction. Why does your database suddenly slow down at 2 a.m.? We are about to find out. In the world of LSM trees, we never update data in place. We only append. This creates a fragmented landscape of multiple SS tables containing overlapping keys and obsolete versions of data. Compaction is the essential background process, the janitor of the database that prevents this fragmentation from collapsing performance. It performs a multi-way merge sort, taking several sorted SS tables as input and producing a single, consolidated SS table. During this process, the engine finally discards tombstones markers for deleted records and purges older versions of keys that have been superseded. Without efficient compaction, the read path would have to scan an ever-increasing number of files, leading to what we call read amplification. This background merge is what keeps the LSM tree's search efficiency within logarithmic bounds. But how does the engine decide which specific files to merge and when? The answer lies in the specific strategy chosen for the workload. There are two dominant schools of thought in compaction: size-tiered and leveled. Size-tiered compaction, commonly seen in Apache Cassandra, groups S tables of similar sizes. Once a threshold of files in a tier is reached, they are merged into a larger file in the next tier. This is incredibly efficient for write-heavy workloads because it minimizes the work done during writes. However, it can lead to high-space amplification because keys can exist in many files simultaneously. On the other hand, leveled compaction, popularized by RocksDB, organizes data into distinct levels, L0, L1, L2. Each level is 10 times larger than the previous, and crucially, keys within a level, except LO, are non-overlapping. This provides much more predictable read performance and better space efficiency at the cost of more frequent merges. Choosing the wrong strategy can lead to a compaction debt that your system can never repay under high load. This choice is the most impactful lever for tuning your database performance profile. In system design, we must account for space amplification, the ratio of the actual size of data on disk compared to its logical size. In an LSM-Tree, since we don't overwrite, a single 1 KB record updated 100 times could technically occupy 100 KB of disk space until the janitor completes its work. In size-tiered systems, you might need to keep up to 50% of your disk space free just to have enough room for the compaction process to run. This is a hidden cost often overlooked in capacity planning. High space amplification isn't just about disk costs. It significantly impacts the efficiency of the OS page cache and increases the time required for backups and recovery. If your data volume grows faster than your compaction throughput, you risk a disk full error even if your actual data volume is well within limits. Understanding this amplification factor is critical for building resilient distributed systems that don't fail under pressure. But even if you have plenty of disk space, there's another tax that affects your users directly. Compaction is not a free lunch. It is a heavy I/O consumer that competes with your application's read and write requests. This is the compaction tax. When the system is under heavy write load, the engine generates SS tables faster than the background threads can merge them. To prevent the system from being overwhelmed by too many files which would destroy read performance, the database engine will intentionally slow down or even stop incoming writes. This is known as a write stall. From a user's perspective, this looks like a sudden, massive spike in P99 latency. In production environments like RocksDB or WiredTiger, managing these stalls is the most challenging part of performance tuning. If you see your disk I/O utilization hitting 100% while your application throughput drops to 0, you are likely witnessing a compaction storm. It's a delicate balance. You need compaction to keep the database healthy, but too much compaction can kill your real-time responsiveness. This brings us to a metric that every senior engineer must master. Write amplification, WA, is perhaps the most critical architectural metric for modern storage. It is the ratio of data written to the physical storage device versus the data received from the application. In an LSM tree, because data is moved and rewritten multiple times through various compaction levels, the WA can easily reach 20 or 30. This means for every 1 MB your user writes, the disk may actually write 30 MB. This isn't just a performance issue. It physically wears out SSDs by exhausting their limited rewrite cycles. We face a three-way trade-off known as the Rorium conjecture: read overhead, update overhead, write amplification, and memory space overhead. You can optimize for two, but usually at the expense of the third. For example, if you want very fast reads, you must compact frequently, which skyrockets your write amplification. If you want low write amplification, you must tolerate more files and slower reads. Understanding where your application sits on this Rorium triangle is the mark of a true storage expert. To maintain a healthy database in 2026, you cannot rely on default settings. You must actively tune compaction parameters based on your telemetry. First, always monitor the compaction pending bytes metric. It is the lead indicator of an impending write stall. Second, set a compaction throughput limit to prevent maintenance from starving the application I/O. Third, consider the size of your memtable. Larger memtables result in larger LR files, which can reduce the frequency of merges. Fourth, for extremely large datasets, sharding or partitioning at the application level can limit the size of the LSM tree and keep compaction times manageable. In high-performance clouds, we also see the rise of remote compaction, where the maintenance work is offloaded to a separate compute cluster to protect the primary node's latency. By mastering these knobs, you transform the storage engine from a black box into a precision instrument. Now that we've seen how LSM trees manage their internal state, how does this compare to the traditional B-tree? Let's build a selection framework to decide which engine is right for your next scale-out architecture. In the world of database engineering, there is no such thing as a free lunch. We call this the Rorium conjecture, proposed by researchers to explain the fundamental trade-offs between read overhead, update overhead, and memory overhead. If you want to minimize read latency, you typically pay a price in update overhead or increased memory for indexing. B-trees, for instance, prioritize read and memory efficiency by maintaining a sorted, packed structure on disk, but this comes at the cost of high update overhead due to random I/O and page splits. On the other hand, LSM trees prioritize update efficiency through sequential writes, but they demand more memory for bloom filters and higher read overhead due to checking multiple S-tables. As a strategic consultant, you must recognize that any performance claim by a vendor is simply a decision made within this triangle. Understanding this allows you to see through marketing hype and evaluate a database based on which side of the Rorium triangle it occupies. But how do these theoretical trade-offs translate into hard metrics when comparing B-trees and LSM trees side by side? Let's break down the numbers in the next scene. To make an informed architectural decision in 2026, we must look at the head-to-head metrics. B-trees excel in read-heavy workloads, where point queries and range scans are frequent, as data is kept in a predictable, sorted order. They offer excellent space efficiency because they don't suffer from the high fragmentation typical of LSM trees before compaction. However, they struggle with high concurrency writes, because each write might trigger a cascade of page splits and random I/O. In contrast, LSM-trees are the kings of write throughput, absorbing massive bursts of data into the memtable and flushing them sequentially. The trade-off is read amplification. The database might have to search through several levels of SS tables to find a single key and write amplification caused by the background compaction process. When choosing an engine, you aren't just choosing a data structure, you are choosing which type of system resource you are willing to sacrifice. But wait, these metrics shift dramatically when we apply them to specific industry use cases like IoT or finance. Is there a clear winner for your specific project? Let's analyze the real-world scenarios. In the field, we categorize requirements into patterns. Consider an IoT telemetry system generating millions of sensor readings per second. Here, the write throughput is the primary bottleneck. An LSM-tree engine like RocksDB or the engine inside Apache Cassandra is the logical choice because it transforms chaotic random writes into efficient sequential disk I/O. Conversely, look at a traditional ERP system or a core banking ledger. These systems demand strict ASI compliance, heavy point lookups for specific account balances, and frequent updates to existing records. A B-Tree engine, like those found in PostgreSQL or Oracle, is superior here because it provides predictable log and read performance and better support for update-in-place operations without the latency spikes associated with LSM compaction. Choosing the wrong engine for these scenarios doesn't just slow down your app, it can lead to catastrophic system failure under load as write stall or compaction lag takes over. But what if your application needs the best of both worlds? This is where the industry is moving in 2026 with hybrid architectures. Now let's explore how modern databases are breaking these traditional silos. By 2026, the strict wall between B-Tree and LSM-Tree is crumbling. We are entering the era of hybrid and pluggable storage engines. Modern systems like PostgreSQL are now being extended with LSM-based storage wrappers for specific workloads, such as pgrocks for high-speed ingestion. Furthermore, the rise of vector databases for AI has introduced multi-tiered storage strategies. In these architectures, hot data is managed by memory-resident B-trees for instant retrieval, while warm or cold vector embeddings are pushed into LSM structures for efficient bulk storage and retrieval. We are also seeing tiered storage where the engine automatically migrates data from an LSM tree optimized for incoming writes to a B-tree or columnar format as the data ages and becomes read-only. This allows architects to achieve high write performance without sacrificing long-term read efficiency. Understanding these hybrid patterns is the key to designing systems that can scale to petabytes without breaking. We've covered the internals and the selection framework, so let's tie it all together. In our final chapter, we will synthesize this into a strategic roadmap that will future-proof your database architecture for the next decade. We have deconstructed the very DNA of database engines, from the immutable nature of tables in LSM trees to the structured page-level management of B-trees. The fundamental trade-off remains constant. You are always balancing write throughput against read latency. We've seen how the write-ahead log or while ensures our durability even when memory-resident structures like the memtable are volatile. In the real world, choosing a storage engine isn't about following a trend. It's about understanding whether your application's bottleneck will be write amplification during heavy compactions or the overhead of random I/O and locking in a B-tree buffer pool. By 2026, as datasets grow into the petabyte scale, the difference between an O1 index lookup and an OG-N tree traversal becomes the difference between a responsive service and a total system outage. This internal mechanics knowledge is what separates a senior architect from a generalist developer. But knowing how they work is only half the battle. The real question is how to apply this to a global scale architecture where the physical limits of a single machine are reached. Every performance problem you encounter in production is almost certainly a storage engine problem in disguise, waiting for you to tune its compaction strategy or page size. Now that we've mastered the vertical scale of a single node, we must ask, how do these engines coordinate across 1,000 nodes without losing consistency? As we conclude this deep dive, your strategic roadmap for 2026 must prioritize workload-aware engine selection. Do not let the marketing of a database brand dictate your architecture. Instead, look under the hood at the storage engine. If you are building high-velocity telemetry or logging systems, lean into the LSM-based engines like RocksDB or ScyllaDB to handle the write pressure. If your workload is dominated by complex range queries and classic OLTP patterns, the mature B-tree implementations in PostgreSQL or SQLite remain your safest bet. However, the industry is shifting toward disaggregated storage, where the engine lives separately from the compute layer, often backed by high-performance object stores. In this new paradigm, the storage engine's role in maintaining local state becomes the foundation for distributed consensus protocols like Raft or Paxos. To build a system that scales to millions of users, you must treat the storage engine as the heartbeat of your system. It must be robust, predictable, and perfectly matched to your data access patterns. This concludes our technical deep dive into the internals. But wait, the storage engine is merely the engine of the car. The steering wheel that guides data across a network of machines is a different beast entirely. Every choice we've discussed today, like Whale and immutability, is a prerequisite for the next major leap in your engineering journey. distributed consensus. In the next chapter, we will see how these local logs become the source of truth for a global cluster, and why your choice of engine will either simplify or complicate your path to high availability.